We are told in this practice problem that we have 100 grams of water and 25 grams of sodium chloride. What we need is the vapor pressure of the sodium chloride solution. Now, the important reminder here is that sodium chloride is non-volatile. So all we need to do this problem is the simple form of Raoult's law, which states that the mole fraction of water times the vapor pressure of water would be the vapor pressure of the solution. So really, since we're already given the vapor pressure of water here, we just need to figure out what the mole fraction is. And so to do that, we need to determine the number of moles of water, 18.02 grams in 1 mole. So 100 divided by 18.02 is the 4 sig figs, 5.549 moles of water. For the 25 grams of sodium chloride, we're told the molar mass is 58.44 grams. So 25 divided by 58.44 is the 4 significant figures again, 0.4278. We need to add those together. And rounding to 3 decimal places because our less precise value is known only to 3 decimal places, we get 5.977 moles. So to do the mole fraction, I need the moles of water, 5.549. Divide by the total, 5.977. And we're going to multiply this by 23.8 torr. $5.549 divided by 5.977. My mole fraction to 4 significant figures, 0.9284 times 23.8 torr. To 3 significant figures, the vapor pressure of the solution would be 22.1 torr. So our vapor pressure is lowered, but not considerably because we haven't added a terribly large amount from a molar standpoint of solid. So any questions with this particular example before we move off of vapor pressure and into freezing and boiling? All right, so I want to start the new topic here with a question also. We've kind of alluded to this already, but I'm interested to see what you've picked up over the past week or so. Based on what we have seen with vapor pressure, based on what we have seen with our other colligative properties, how would we expect the freezing point of a solution to change compared to the solvent? How would we expect the boiling point to change compared to the solvent on its own? So go ahead and put in your ideas here. And let's see what we can come up with together. All right, give you another minute or so to put something in here. Okay, so the general gist that we're putting out here is that we know both are going to change. If I had to kind of take a group consensus, we would say that both of them would increase as a result. And the answer there is, well, you're half right. We saw from vapor pressure that we know that vapor pressure is going to decrease by the addition of a solvent. So naturally, we know that that means that the boiling point would increase as a result as well. But we have to look at it from the other standpoint as well. Why is it increasing? It's because the intermolecular forces are stronger. And stronger intermolecular forces mean that it's going to be more likely to stay a liquid longer, which means that the freezing point isn't actually going to go up, it's going to go down. And from a phase diagram standpoint, so the two answers here that we would end up looking for, if we're looking for kind of pure definitions, boiling point elevation, the boiling point increases as a result of those increased interactions between solute and solvent. And freezing point depression, the freezing point decreases as a result of those increased attractions between solutes and solvents. And this kind of manifests itself in the form of a phase diagram where we can see that if we look at our solution here, which is shown by the darker lines on the phase diagram, relative to the pure solvent, which is shown by these lighter lines, we can see that the liquid region of our phase diagram has expanded as a result of solution making. So the aqueous solution is going to generate a larger liquid region and smaller gas and solid regions as a result of these increases in intermolecular force. We can quantify these changes using these two equations. And the difference here, what we're talking about are changes. So the Greek letter delta here indicates that we have a change occurring. So delta TB indicates a change in TB, TB being the boiling temperature of our particular substance. Delta TF would indicate a change in TF, TF being the freezing temperature of our substance. And so we can see that the changes in those temperatures depend on three factors. And you know these three factors already, well, at least two of them. One, the Van Hoff coefficient, the Van Hoff factor. We talked about that on Monday when we talked about osmotic pressure. The second, molality. Talked about that last Friday. And the reason we use molality there, lack of temperature dependence. Molality does not change with temperature. And then the last factor here, K. K is a constant, and it is unique to a given solvent. So every solvent has a unique value of Kf and Kb. Kf would be its freezing point constant. Kb would be its boiling point elevation constant. And those values are reference values. You can find them in reference tables. Once again, Van Hoff factor, that's going to come in particular when we are looking at ionic substances. So when our substances are non-molecular, when they are ionic, Van Hoff factor is going to be used to quantify how many particles there are in the solution and account for more drastic changes in those particles as a result. Here's a common table of values for Kf and for Kb. You can see that water has a Kb value of 0.51 degrees Celsius per molal. So for every 1 molal of concentration in the solution, that boiling point is going to go up by about half of a degree. Its freezing point depression constant is 1.86 degrees Celsius per molal. For every 1 molal of concentration, the temperature of the freezing point is going to go down by about 1.86 degrees. And then we have our normal boiling points and our normal freezing points, because if we are asked to actually determine the freezing point of the solution, not just how much the freezing point changes, then we need to either depress the freezing point, so take whatever that delta T is and subtract it from our freezing point. Or for the boiling point, we take whatever that delta T is and add it to the boiling point. Let's take a look at an example here. What is the boiling point of seawater in which the concentration of sea salts is equivalent to 0.560 moles of sodium chloride per kilogram of seawater? And the Van Hoff factor for sodium chloride, 1.85. Okay, so two things that we need to identify here. First of all, we are looking for the boiling point, not just the boiling point elevation. So we're looking for TB, not delta TB. Important distinction there. Because delta TB gives us half of what we need. We're going to have to add that to the boiling point of water. Using the equation, delta TB is equal to I KB M We are told that the Van Hoff factor is 1.85, so that's our I. KB, we can pull from that table. KB for water is 0.51 degrees Celsius per molal. And then the molality itself is this 0.560, because we already have moles of sodium chloride per kilogram of seawater. That by definition is molality. We don't have to do anything with it. So if I follow through in that calculation, 1.85 multiplied by 0.51 multiplied by 0.560 to two significant figures, I get 0.53 degrees Celsius. Now, probably the most common mistake that students make with these kinds of problems is stopping here and saying, okay, the boiling point of the solution is 0.53 degrees Celsius, I'm done. Well, you take a second and think about that. That doesn't make any sense. How does water, which normally boils at 100 degrees, now only boil at 0.5 degrees? Doesn't quite make sense, doesn't add up. That's because you forgot to add it up. The boiling point of the solution is equal to the boiling point of the solvent plus the boiling point elevation. Boiling point of the solvent is 100 degrees Celsius. And yes, I can use as many of those decimal places I want. The boiling point of water is defined at 100 degrees Celsius according to the thermometer. That's how the thermometer was made. So from that standpoint, we don't have to worry about significant figures. We can just add these two together. It's 100.53 degrees Celsius. So that is the boiling point of the solution. And now we look at it from that context and, oh, that does make sense. My boiling point went up. It was 100, now it's 100.5. All right, any questions about this problem? All right, let's take a look at another one. Calcium chloride is widely used to melt frozen precipitation on sidewalks in a winter storm. Could calcium chloride melt ice at -20 Celsius? Assume that the solubility of calcium chloride is 70 grams per 100 grams of water, and the Van Hoff factor is 2.5. Okay, this is a little bit more complex of a problem, but it's still doable. We just need to know what it is that we are doing. So ultimately, we can approach this in one of two ways. We can either start with our value here and say, okay, that means that the freezing point depression has to be 20 degrees. And then work backwards to figure out what the molality of the solution would be for that particular freezing point depression. The other way, though, the way that probably makes a little bit more sense is let's take all of this information that we have and turn it into a freezing point depression, and then turn it into the freezing point of the solution, and we can compare it to the -20 degrees. And if the depression is greater than 20, then we know that the answer to the question ultimately is yes, it will. So to do that, I need to do one little thing. That is a mass percent. not a molality. So I need to take my 70 grams per 100 of water and turn it into moles over kilograms of water. 70.0 grams of calcium chloride. Calcium is 40.08. Each chlorine is 35.45. So 110.98 grams in a mole. 70 divided by 110.98 is equal to 0.631. That's how many moles of calcium chloride I have. So molality is 0.631 moles over 100 grams is 0.1 kilograms. So the molality of the solution here is 6.31 molal calcium chloride. So that's my molality. And now I have everything I need to solve the freezing point depression. Remember, it's I times Kf times M. My I factor here is 2.5. My Kf is 1.86 degrees Celsius per molal. And my molality we just calculated 6.31 molal. My freezing point depression, 2.5 multiplied by 1.86 multiplied by 6.31. Two significant figures is 29 degrees Celsius, which means my freezing point would be 0 degrees Celsius minus 29 degrees Celsius, which would be negative 29 degrees Celsius. Question asked if it could melt ice at negative 20. Answer is, yep. In fact, it could melt ice all the way down to negative 29. Now, if you get below negative 29 degrees Celsius, you're not going to be able to use regular old road salt. You're going to have to do something else, probably hunker down indoors, because that's pretty darn cold. All right, any questions with this example either? Okay, so in the interest of time, I'm going to skip the next two sample exercises, and when we come back to this on Wednesday, we might just do one or two of them as kind of a review, just to kind of get us back into the flow of things after the exam. I do want to take this last minute or so and talk about one other concept, and that is Henry's law. Now, Henry's law is something that is used to quantify the concentration of gases in liquids. And you can see it's got a very nice equation here. We don't need to worry about the equation. We're not going to do any Henry's law calculations. What we do need to understand, though, is that there is a relationship between the concentration of a gas and the pressure of the gas above the liquid. Now, you experience this particular phenomenon on a fairly regular basis, because the whole idea of bottling is built on this very premise. There. The The soda and seltzer industry is built entirely on getting carbon dioxide, which is not soluble in water, to dissolve in water. And how do they do it? They pack that bottle so full of pressure that it forces the carbon dioxide into the liquid. And they keep it cold because everybody knows cold beverages taste better than warm ones anyway. And also because solubility-wise, when the temperature increases, the solubility of the gas decreases as well. So between the two, that's when we can maximize the solubility. But you know, as soon as you open that bottle, what's the first thing that happens? The whole thing starts to fizz up. All that trapped carbon dioxide starts to bubble up to the surface because we've released the pressure and now it's not as soluble as it once was. And so when you open a bottled beverage of this kind, time is always of the essence. The longer it sits out, the flatter it gets because it gets warmer and because it starts to equilibrate to the pressure above it. So when you think Henry's law, this is what you need to think about, because this is kind of the easiest example for what two relationships exist. So I wanted to leave with that note and get your feedback on the way out the door. If you're coming to the study session this afternoon, I will see you there. Otherwise, have a great weekend, and I'll see you on Monday for the exam.